Okay, welcome back, everybody. Let's see how this goes. My voice, I don't know, you can tell, but my voice changed a little bit. I woke up this morning with a little bit of a head cold. So I guess the plan would be first to finish this chapter out and then things out to see how things go, and then we'll continue. If not, maybe we'll just continue next Wednesday. But I will, on Friday, we're dealing about gases. There's a chapter, the last chapter, the semester, chapter 16, that deals with gases. It's very short. I probably will introduce that in the lab because it's kind of tied into the next experiment that you'll be doing. Okay. So any questions, comments, concerns? No? All right. Well, then let's continue where we left. According to my records, we were in chapter 5, and we are on slide 19. Now, what is going on here is we are talking about the electrons and where they exist within the atom. So let me back it up a little bit and go over briefly where we're at up to this point with respect to the atom and the model that we have of the atom. And so we started off way back with J.J. Thomson. His work demonstrated a charged subatomic particle, which later on became known as the electron. So he's responsible for that. And then you had Ernest Rutherford, who was doing an experiment where he was bombarding gold atoms with particles, and then he was expecting them to just go right through the foil, and that was the end of it. But what he was finding is some of the particles he was bombarding the gold with were actually being ricocheted off. So he concluded that there's got to be a center moiety in the atom that's very, very dense, much bigger than the particles that he was shooting at. Okay, so then in the 30s, Chadwick was the one who's credited with discovering the neutron. So we got the Rutherford, who's credited with the neutron slash nucleus, Chadwick with the neutron, and then J.J. Thomson with the electron. So the model up to this point is that in the center, there's the nucleus where the proton exists and where the nucleon exists. And in some place around the atom, the nucleus, existed the electrons. Okay. Well, the electrons being so small, literally with a AMU of 0, being so small, they exhibited properties of light and they behaved like light. So we went through an exercise of understanding light a little bit and how it travels and how light has a very specific energy level. Okay. And so the later scientists like Bohr came up and said that the electrons, as actually Planck, who talked about quantum specific energy levels, and then Bohr borrowed from him and said that the electrons are specific, they exist in specific energy levels. And that was determined by taking gas, basically fluorescent light bulbs, but the bulbs were evacuated, and in there was placed whatever atom or element they're looking at, then exciting it. They exhibit light, and once they exhibit light, that light went through a prism. A prism is a piece of equipment that takes light and breaks it up into different wavelengths, just like the raindrops do to break up the water and the light into different wavelengths that give us the rainbow. So in doing that, it created the light emission spectrum for that element. Okay, very specific lines of wavelength of energy at specific lengths, and you can back calculate that and figure out where those electrons initially existed. Okay, so then the model becomes that we have 7 energy levels. Okay, 7 energy levels, which, if you look at the periodic table, it's labeled, and we call those the periods. So it's we have 7 horizontal lines across the periodic table. Okay, and those represent the energy level. So you got the first one that you have. Let me pull up the periodic table real quick. And so here you have, 1 second. You have the first energy level right here. Number 1, that encompasses the electrons from hydrogen to helium. And then the second energy level, starting with lithium across to neon. And so those electrons, well, I'll come back to that in a second. And then the third energy level, from starting with sodium to argon, and then all the way to the fourth. We'll stop at the fourth. Okay. And so the electrons for hydrogen and helium exist in the first energy level. Okay. And then the electrons starting with lithium all the way across the neon, yes, they fill up the first energy level, you know. And so, like, for example, lithium has three electrons total. Well, the first 2 get filled up in the first energy level, and then the one that's left moves up to the second energy level, and so on and so forth. So we go across the periodic table, okay, to fill up the electrons. All right. So, all right. So within these energy levels, then there are sub levels, which are called orbits. Okay. And the first one, the orbit is given the letter S. That's the S orbit. And then the P is the second type of orbit. And specifically, let me back up. In the S orbit, there's only one. All 7 energy levels have the S orbit. So those are denoted by 1s, 2s, 3s, 4s, all the way to 7s. Okay. In the second energy level, you have the 2s, okay, but we start introducing what are called the p orbits, and there are specifically 3 orbits in the p orbitals, okay. Each orbital can handle a maximum of 2 electrons. Therefore, the S can handle 2 electrons maximum. Once that's full, if an element needs another electron put someplace, it must go to another orbit or another energy level. Okay, so you sequentially fill up the electrons in the different energy levels, starting with the lowest and working your way up. Okay. The D, there are 5 orbitals of the D, and each one can handle 2 electrons. So for all D orbitals, they can handle a maximum of 10 electrons. And then finally, the F orbitals have 7. There's 7 F orbitals, and each one handling 2 maximum electrons. They can handle a total of 14 electrons maximum. Okay, so that is the maximum electrons that each orbit can handle. Now, a side note here is that these orbits, where they come from are the mathematics of the whole thing. This model was placed was formulated from mathematics, okay, and very sophisticated, very big mathematical equations. And what happens is for the S orbital, you plot data in the S orbit. It's just an equation. You can plot it in the 3-dimensional, and you end up with an image. And the same is true with the P, the D, the F, and so forth. But there's no right at this point, we're only going as high as the F. Okay. Now, this level really, I think, keep me to kind of flip this upside down, like an upside down pyramid, because you're actually, when you start filling electrons, you're filling them up at the first level, and then you work your way up. So in the first level, which encompasses simply hydrogen and helium, okay, there's only one level and one orbit. Let me, okay, and we can denote that by writing an arrow. Let me change the color here for a second. All right. Okay, so I can make an arrow here. Okay, Now, what that arrow does represents one electron in one direction. It's orbiting around a certain direction. So that's hydrogen. Hydrogen's only got one electron. And now, if we go across the periodic table from hydrogen, like I demonstrated earlier, all the way across to helium, helium's got two electrons. So its second electron can only go, you need to fill up the orbital. And so we can denote that by, the first one was hydrogen, okay? And then the second one is helium. And that helium has two electrons. Those two electrons exist in the 1s1, 1s2 configuration. Let me back up for a second. Now, to show the electron configuration, we use the following notation. Okay, we'll say here for hydrogen, we write 1, which represents the first energy level, and then the orbital, which is S. And then we do a superscript on the orbital, in this case for hydrogen, of 1. Okay, that is called the electron configuration for hydrogen. Now, when we go across and we go over to helium, well, helium now has picked up a proton and it's also picked up an electron. So helium now has 2 electrons. So we can denote that by 2 arrows going opposite direction. We're talking about helium. And this 1 becomes a 2, okay? So that is the electron configuration for helium. Now, if you got your periodic table in front of you there, go around to element number 3, which is lithium. First of all, note that lithium is the second energy level. And so there's 3 electrons that lithium has. The first 2 are filled up. Now, before I go on, the reason I wrote the electrons in different directions within the box is simply this, based on the mathematics, is when you have 2 electrons in one orbit, they don't orbit in the same direction, they go an opposite direction. That's why I got them written in different directions. Okay. In fact, if the orbit is changing one, the other one, if it has another one, simultaneously changes to go the opposite direction. Quite crazy. All right, so now going into lithium now. Lithium, okay, if you find it in a periodic table, it's in the second energy level. Now we're going to talk about the electron configuration. There's 2 ways to write the electron configuration. There's the way the book gives you, which is just the equation and the numbers that you just fill up sequentially, and that's fine. You can do that. But I like to use the position of the periodic table and very quickly, based on the position of the periodic table, tell you write out the electron configuration. All right, so and let me do this, because before, let me go back to the periodic table. Okay, now the first 2 columns, okay, think of these as the S elements, okay, S elements. There's 2 columns, so the first column would be S1 if I got 1 electron, and then the second column would be S2, okay, because we're going across the periodic table. So these are the S elements. So then we shoot all the way across, and we go across over here from group number 3A all the way to 8A. Think of those as the P elements. And note there's P1, P2, all the way across to P6, 6 columns. You've got S1 over here, all the way to S2, okay? And so, for example, going back to the S elements of calcium has being in group number 2, being an S2 element, the 2 electrons on the outermost shell will exhibit in the S orbital and have superscript 2, okay? We go across the periodic table, then we enter the domain of the P. All right. Now, these guys in here, which they have their own specific name, we're going to learn about them down the road here. Think of these as the D elements. Notice that in the D, In the S, we have 2 electrons, okay? We can maximum 2 electrons. So we got S1, S2, superscript. We want to fill up those electrons. And the P, we can put in a maximum 6 electrons. So we go P1 all the way across to P6, okay? And then the D has a total of 10 electrons. And we can go starting with number 21, excuse me. This could be D1, go all the way across to D10 for zinc when filling up those electrons. Now we're going to learn that for the D elements, not all of them are sequentially going 1, 2, 3, 4, 5, and that is true. However, for Chem 130, we're just, because it's beyond the scope of Chem 130, we can discuss them if we want, but it's not necessary. We're just going to call it from D1 across to D10. Okay. Then the ones down at the bottom just stick out here, and they also have their own specific name. Call these. Think of these as the FF electrons, and there should be 14 columns from F1 all the way across to F14. Okay, so with this information, knowing the energy level that it's in, you can very quickly write out the electron configuration for any element given, okay? Or you can, memorize it like the book gives you, and that's fine. But this, for me, is just using this position periodic table. I think a lot more. I think it gives you a lot more grasp on how these electrons are put together and assembled. Okay, now go back. And so we went across the hydrogen and filled that up. And it was helium. Okay. So that level, the 1s2 is filled up. So actually I can put it right here, 1s2. Okay. Now I go to lithium. This is the 2s and the 2p. Lithium is first group, like I just stated, group number 1, Roman number 1a. S element. So its electron gets placed in the S orbital. Okay. Then we move across to right next to lithium is beryllium, Be. It has a total of 4 electrons. Okay. So again, being an S electron, and in the second column, we fill up the first one, we put a 1 there for boron, but then when we fill up beryllium, that 1 becomes a 2. Okay. So the superscript represents the number of electrons. It has beryllium has 4 electrons. Okay. Let me write this longhand. So it's 1s2, 2s2. This is beryllium. It has a total of 4 electrons. Of those 4 electrons, 2 of them are in the outermost energy level. We call that the valence shell. Valence shell. And then the other 2 exist in the inner shell. They're covered by the energy level number 2. We call those the core electrons. Okay. Now, when it comes to reactions, keep in mind that all reactions occur with the exchange and the interaction of the electrons in the outermost level, the valence shell. That's where all the actions happen. And how many electrons they have in the outermost shell dictates as to what type and how a reaction is proceeding, and whether an element will give up electrons or gain electrons, because the ultimate goal for all of these elements in any chemical process is to obtain the 8 electrons on the outermost shell. Okay. All right. So now this represents beryllium. And if we go across the table, we have a new boron, which I'm going to replace this. Boron now has 5. This is boron. There are 5 electrons. Well, the 2 are in the 1s2, but then the 2s2 is full. But now the only place, remember, boron is over across the 6 columns of what I call the p electrons, p1, p2, p3, etc. And so the other electron will go into p orbital. So its electron configuration would be 2p1. Okay. So again, its outermost shell contains 3 electrons. 3 electrons. And if you look at the group number, the Roman numeral 3a, that tells you there's 3 electrons for all those elements in that group. Okay. Okay. Now, as we continue to the next atom, which will be carbon, as we continue, which will be carbon. Okay, let me clear this up. Now we end up adding another carbon. Now I don't put it in the same box. I put it in another empty box. Again, the mathematical rules tell us that when we have multiple orbitals, we fill up every orbital first before we start doubling up. Okay, so this now becomes a 2, and this represents carbon. Okay, carbon is element number 6. Okay, element number 6. Carbon is in group 4A. Look on top of that whole group, 4A. That tells you there's 4 valence electrons for carbon. And here they are. 2 of them are in the S and 2 of them are in the P. Okay. Now we continue the process, and nitrogen. See, I'm not changing much of anything. I'm just changing the superscripts. Nitrogen now has, there's a total of 7 electrons for nitrogen, of which 5 of them are in the outermost shell. Those 5, 3 of them are in the p orbital, 2 of them are in the filled s orbital. Okay. The order of adding the electrons is s, p, d, and f. So within the same energy level, the s electrons are a little bit lower in energy than the p, which are a little bit lower in energy than the d and the f respectively. So within the energy level, you can put it, the s gets filled first, then the p's, and then move on to the d's, and then necessarily move on to the s. Okay. All right. So now you're still going to shooting across the periodic table. Okay. Correlating the number of valence shells with that Roman numeral on top of the group number, and showing you how that Roman numeral corresponds with the outermost electrons that it has. Okay. Now go to the next one, which is oxygen. Well, oxygen, let me clear this up a little bit. Oxygen has 8 electrons. Okay, so since all the p's are full, now I can start doubling up on the orbitals. Okay, there's oxygen. Oxygen is in group 6A, Roman numeral VI 6A, which tells you that there are 6 valence electrons. See, 4 plus 2, 6. Okay, those 6 valence electrons, we have 1, 2, 3, 4 of them exist in the p orbital, which is not empty. Okay, it has 2 empty slots, and the s orbital of the second energy level, which is full. Okay, I'm hoping that you see a little trend here. Is this when we were dealing with metals, like we did over here with lithium and beryllium, and the outermost shell, they had electrons, basically they're all by themselves. Okay, and if you recall, I stated that all metals want to lose electrons. So all metals want to lose electrons because they don't want to maintain those electrons that are way out there in the outermost shell by themselves. But as we progress across the periodic table, we start going into the domain of the nonmetals like nitrogen here and oxygen. You can see that oxygen has room for 2 electrons. I'm going to denote those by the dotted arrows. One there and one there. Okay. Notice that nitrogen had room for 3 electrons, and oxygen, go across the periodic table, has room for 2. Fluoride would have room for 1, but let's stick with nitrogen right now. And so oxygen is a nonmetal. So oxygen has a tendency to gain electrons because it has room, denoted here by the dotted arrows. It has room for electrons, specifically 2 of them, okay? And so it will strive to obtain 2 electrons to fill up the outermost shell. Because if those 2 dotted arrows are full, guess what you have altogether now? You have 8 electrons around the outermost shell. And that is the magical 8, if you will, that atoms are striving for to obtain the number of electrons that give you 8 around the outside orbital and put it more in a more stable position, okay? And so in essence, with oxygen, by the fact that it can easily gain 2 electrons, it will have an overall -2 charge, right? Now think about that, because oxygen has 8 protons and 8 electrons as an element. So 8 and 8, 8 negatives, 8 positives, okay? Net 0. Well, now if it gains 2 electrons, now it has 10 negatives and 8 positives. So the overall net gives it a -2 charge, okay? So if oxygen were to gain 2 electrons, it would become what we call an ion, ION. And it's no longer the element, it has become an ion, but gaining 2 electrons. That is what we ingest as humans. That's what happens out here in the world, is we're dealing with ions, okay? Even our body is full of ions, which are nothing more than the elements that either have gained or lost electrons, so we end up with a charge, either a positive charge or a negative charge. And those are the components that work for us, are very important, because without those ions, our body, for example, could not create electrical charges and signals to go from point A to point B, because these ions carry the electrical charge from one point to the other. Okay, so hopefully you can start seeing here the driving force. So that's oxygen. Now let's move in from oxygen to fluoride. So fluoride, get this out, fluoride. Okay, well, guess what? We just fill one of these up. Okay, this 4 becomes 5, and that's 5. Okay, let me erase that a little better so you can see that right there. So it's 2p5, 2p5. Okay, now if you look at the group that fluorine is in, it is in group Roman numeral 7, which tells you there are 7 valence electrons on the outermost shell. Okay, 2 of them are in the s orbit, and the other 5 are in the 2p5 orbital. It still has that dotted spot, so it can gain 1 more electron. I left that dotted arrow there on purpose to demonstrate how fluoride, like oxygen, like nitrogen, they tend to gain electrons because the outermost shell is full to reach that magical 8 number. And so if fluorine were to pick up an electron, okay, it then becomes a -1 charge because it picked up 1 electron. And that 1 dotted arrow there, it has room for 1, so that's where it exists. So now it contains 8 valence electrons, which is analogous to the valence electrons for the noble gases, which are in group 8A. All those noble gases in the right column, they have obtained 8 electrons around the outermost shell, except helium. Helium's got 2. Helium's magical number is 2, but everything below that, neon, argon, krypton, xenon, etc., they have 8 electrons. And that is why those noble gases are called noble gases, because they tend to be unreactive. It is difficult to do anything with an atom that has 8 electrons around it. they hold on to those 8 electrons very tightly, and you can't really put one off. And you really can't put one in, because if you put one in, then it's violating the octet rule, and the only place it can go would be the next energy level, which is not very stable. Okay. All right. So that's how you make fluoride, and that is what you're brushing your teeth with in the morning. If you use fluorinated toothpaste, you are brushing your teeth with maybe sodium fluoride. Excuse me. Sodium fluoride, or what's called stannous fluoride, SN, which is tin, TIN fluoride. There are a salt. We call them a salt. Okay, remember that the term salt does not just represent sodium chloride by itself. Salt is any combination of a metal and a non-metal, like sodium chloride. Sodium is a metal, chloride is a non-metal. Okay. All right, then finally, we're still in the same group. Notice we haven't done it. We're still in the same group. We're finally at the end of the rope here, so to speak. And we end up with a neon. Neon has 10 electrons. And it's in, the last column of the P element, so it's P6. All right. Let me clean this up a little bit here. The 2. Okay. And so the electron configuration for neon is given as follows: 1s21, which is that first energy level, 2s2, which is the s orbital of the second energy level, and 2p6. Okay. Notice, counting the superscripts, 6p electrons and 2s electrons tallies up to 8 electrons in the outermost shell, which is the second energy level. Okay. And so that is why neon is very unreactive, because there's 8 electrons around it. And the same would be true for argon, be 8 electrons around it, but it'd be in a higher energy level, okay, which is area number 8. And that's why they have in common. That's why they put in the same group, because they have properties. All the A elements are in the same group, because they share the property of the same number of valence electrons in the outermost shell. Everybody in group 1 has 8 valence electrons. They're being different energy levels, energy level 1, 2, 3, 4, 5, but they all share 1 valence electron in the outermost shell. Okay. And then everybody in group 2A share 2 valence electrons, and so on down the road. Group 3A, etc., all the way down the road to group 8A. Okay. And so the driving force again is that we just did fluorine. If fluorine can pick up 1 electron, then it has the same number of electrons. See, fluorine has 9 electrons to begin with. 9 electrons. And if it picks up 1 electron, then now it is what we call isoelectronic. Isoelectronic. Which means the same number of electrons. Okay. Oxygen needs 2 electrons to become isoelectronic with neon. Fluorine, 1. Nitrogen needs 3. So we got, let me clear this up a little bit, and we'll go to a slightly different color. Okay. So nitrogen, being in group 5A, has 5 valence electrons, so it can pick up 3 valence electrons, okay? 3 electrons, okay? Oxygen, everybody in group 6, can pick up 2 electrons, and then everybody in group 7A can pick up 1 electron, okay? Because starting with group 5A, there's room. First of all, it's a non-metal, and there's room for 3 more electrons. Okay. The result being is that the ions that are formed, nitrogen on down here, are called, have a negative charge, -3 charge, okay? And oxygen, sulfur, and selenium, etc., have a -2. And the ones in excuse me one second. Somebody's at the door. Can we just pause for a minute? Okay, I'm back. Sorry about that. Just had a delivery. So as I was stating, the ones in group 5A, B nonmetals, they are going, let me clear this up somewhat. They are going to have a new net charge of -3. Group 6, -2, and group 7, -1 to form these ions once they pick up electrons. And that's true for everybody in here. They're highlighted. Okay, all these nonmetals. Okay, and again, by doing that, by gaining 3, 2, or 1 electrons, now they are isoelectronic for the ones in group in the second period for nitrogen, oxygen, and fluoride. Now they're isoelectronic with neon because they share the same number of electrons. The phosphorus, the sulfur, and the chloride are isoelectronic with argon, okay, because now they share the same number of electrons. So that is the driving force to get that magical 8. On the other hand, on the other side, the nonmetals, they got 1 valence electron, okay? Like sodium, there's 1 valence electron. And the next layer in is full, okay? So by losing 1 electron, the new layer in, okay, which is in the second energy level, is full and has 8 around it. So losing here, I'll do it here, 1s2, 2s2, 2p6, 3s1. That's sodium, electron configuration. Sodium is in group 1A and has 1 valence electron, okay? It has a tendency to lose that 1 electron, okay? From an energy perspective, yes, in the third energy level, there's more orbitals, but to pick up more orbitals, just energetically stating was not very practical, if you will. It's quite easier to get rid of the electrons. So in doing so, guess what? For sodium, by losing that 1 electron, now it's new outermost shell, it's new valence shells in the second energy level, and it's full. So it also becomes isoelectronic with neon, okay, with the metal. So as a general guideline to help you out, the metals that by losing electrons become isoelectronic with the noble gas behind it. So sodium becomes isoelectronic with neon, and the nonmetals by gaining electrons become isoelectronic with the noble gas in front of it. So nitrogen, oxygen, and fluoride become isoelectronic with neon, okay, because they share the same number of electrons. It's important here, they do not become neon, okay? So that would be an incorrect statement to say that fluorine becomes neon. Nonetheless, it gain a proton, because remember, a proton defines what the element is. So highly unlikely that fluorine will become neon, but it will definitely become isoelectronic with neon. They share the same number of electrons. All right, so let's go back. All right, so then we continue. We're filling up the sequence. So we were at the first, we're at the second energy level. And these boxes represent, like I stated, each orbital. Notice the P had 3 orbits. So 3 boxes. I can put 2 arrows in there to represent 2 electrons in every box. Now, the confusing part comes into play with the Ds. Okay. And the best way to demonstrate that would be the periodic table, for example. and we have the energy level 1, 2, 3, 4. All right. And now earlier I stated that these guys, think of these as the D electrons, starting with D1 all the way across to D10. Okay. Now you don't have to worry about these until you hit these elements themselves. Okay. So when you hit element 21, now it is the first column of the D. So it'll be a D1. The situation is this: the mathematics of the whole quantum mechanics scenario says that the energy level for the D electrons, for starting with number 21, for example, are not in the fourth energy level, as one would predict, because 21 is in the fourth energy level. They are actually, those orbits actually come out one energy level less. So they actually come out as a 3D. So all the way across for this whole group would be 3D1 to 3D10. 3D1 across to 3D10. If we were doing number 39, for example, it's the same scenario. It would be 4D1 across to 4D10. That the D orbits for number 90 for Y don't show up in the third and the fifth energy level, but actually show up in the fourth energy level. And the mathematics dictate that their energy level is much less. Okay, so that is why you see that the D's show up here. But keep it in mind, in the third energy level, these guys belong to the elements in fourth level. Okay, and the same is this one here, elements in the fifth level. Now, to compound it even more crazier, it comes the F. Okay. Now, even though they got 4F, these F electrons come in 2 energy levels in than the energy level it's at. So actually, these come from the 6th level elements. Okay. But you don't have to worry about them till you actually hit in the 6th level. For example, go back to the periodic table. Okay. This is 6 and this is 7. Notice this is 58, and then it goes to 59 here. So when we start working here with these guys, we will expect, 6F1. That what is anticipated because it's in the 6th energy level, but that's not the case. It's actually in the 4F1 because it's 2 energy levels less. And the same is true for the next one down. This would be the 5F. Okay, compare it because this is in the 7th energy level, but it's 2 energy levels in. And that's the only ones that are a little bit different. All the other ones, the S and the P, whatever energy level in, that's their level. It's just the D's are 1 in, 1 energy level less. The F's are 2 energy levels less. Okay, but you don't have to worry about them until you actually hit the element number 21. If you're asked to do the electron configuration for 21, then keep in mind these are D's, and this will be the last configuration that you will write. We have 1, 2, 3, and 4. This would be 3D1. Okay. Now I will have a slide here to kind of summarize all that for you here in a bit. Now earlier I stated that each orbit can handle X amount of electrons. The X amount is maximum amount is 2. The P's can give you a maximum amount of 6. The D's 10 and the S 14. Okay, but if you ever asked the question, what is the maximum number of electrons for level 2? What would that be? What do you guys think?
Is it 8?
Yeah, exactly. because you can put 6 here and 2 here, and that gives you 8. What about for level 3?
18.
18, you can put 10 here, 6 here, and 2 here. So the maximum number of electrons for the third energy level is 18. Unlike the question being the maximum number of electrons for D, which would be 10 electrons, okay? So note the differences, so make sure you read the question carefully. And then finally, this one, you can see here, you can count them up, it should be 34 electrons. So in the fourth energy level, you can put in a total of 34 electrons. All right, so let's do that. As I stated earlier, that these orbitals come from mathematical equations. And when you take that data and you actually put, if you take that equation and put data into that equation, you actually get a plot. And the plot that you get will look similar to this, okay? Each little blue dot represents an area where you find the probability of an electron being in that area. So obviously where it's darker in blue or aqua colored, you higher probability than somewhere up in the outside where it's not as dark, okay? The trouble with this is that many scientists, including myself, have a problem with this on model. But don't get me wrong, I'm not saying this model's out to lunch. It's the best model we got to date, okay? It just has to be refined. Any model that we have, anything that we look at, always is always open for improvement. And as more work is done and we get better with our equipment and so on and so forth, we tune up the model. Because in one moment, earlier we talked about the electrons and we said, okay, the electrons are in very specific energy levels. Okay, and that's true. We demonstrated that with the line spectrum data. But then we come back and we talk about the probability of an electron being in one spot, okay? And like here, so in one moment we're talking about, throwing the dice, and another moment we're talking about, no, it's a very specific energy level. We got to find something that kind of meshes the two. But at the time, like I stated, it is something to look at. For example, here, these are the models of the images of the p orbits. Those are called the dumbbell. There's 3 of them because of the 3 axes, X, Y, and Z. Okay. And so the first time I saw this and we talked about the probability and I was learning about this, my first thought was, oh, okay. This tells me that in the center where the nucleus is, there's be 0 probability of an electron being there, which is a true statement, okay? Because you got the nucleus there and the electron being in that area just not very high. And so if that can handle 2 electrons, what is happening to the electrons? Are they just hanging out in the lobe there, or just standing still? Are they orbiting? Are they moving around? How are they getting from point A to point B? Hasn't been answered yet. It may have. I haven't kept up on the physics of it. I have to go back and check on it. Some people talk about quantum tunneling, where magically electrons can move from point A to point B without going through it. They just pop up in that area. So, okay, all right. So here's some pictures of the different types of the orbits. The first one is the round ones, the spherical shape, and these are the S orbits. Okay, and then we got the P orbits that you're familiar with, and then we got the 5D orbits. There are some crazy looking shapes here. Okay. And different axes. And then finally the F orbits, again, look like something from outer space. But that is what the models are given the mathematical equations that come up to explain how electrons behave and where they're at in the atom. Okay. Clear my screen here. All right, now, in filling up these energy levels, like I said, to make the electric configuration, you have what your book gives you, basically the order in which you fill them up. And this diagram here depicts that. So it starts off with first energy level, filling up electrons here. The superscripts are left off. It's for you to add superscripts to depict how many electrons for that orbit. Keep it in mind that the S has a maximum of 2, the P maximum of 6, the D maximum of 10, and the F maximum of 14. Okay. So as with anything, you always start with the lowest level, which is the 1s level, and you fill that up. So you're going across the periodic table, starting with hydrogen. Hydrogen is 1s2. Shoot across to helium, 1s1. Let me write that. And so you go 1s, for example, and then superscript 1 for that's hydrogen. Okay. Now, when you move up to helium, it becomes 1s2. Okay. And now you flip around and you go all around to number 2, second energy level, which is lithium. Lithium, that's the second energy level. So that means that you're gonna use the 2s and the 2p possibly as you go across the elements. But, and I write that 2s, 2sp down quickly because I know I may expect some p orbits, but the thing to remember, you go into the far left. So the far left are the 2s elements, okay? So you're not going to fill up any p's until you get across to boron. So the very first one for lithium will be 2s1, okay? It's in the first column. Its outermost shell is energy level number 2, and there's 1 electron in the outermost shell, okay? Once lithium is done, you shoot up to beryllium right next to it, its neighbor, and this becomes Be. This becomes 2. Okay. You haven't reached the P yet. Okay. So I don't even have to write the P down, but I wrote it down for demonstration purposes until you get into way over to the group 3A, which is boron. And that's, you got 6 columns, P1, P2, all the way to P6. So boron, that's where the P orbits start to get filled up. And that moved right up. Notice how we're filling this out sequentially as you go across the periodic table. Okay. And then from P1, which is boron, you can shoot all the way across to neon. We're going to not stop in between because the others in between are just basically changing the P superscript to 1, 2, 3, 4, 5, and 6 until you're done here at neon. That's the electron configuration for neon. Okay. When you, let me change something here real quick. When you come around, hopefully you got your periodic table. When you come around, for sodium, which is in group 3A, that's where the 3 starts to fill up. And then again, like we did with lithium, it's the first column, so it's bam, that's sodium right there, Na. Yeah, and you continue that sequentially. Right? That's the order I've been filling them up right there. And as I stated, you can use this sequence here, keeping in mind that they throw in the 3D in here right away. Okay, but that is when only you hit element number 21, the D elements. All right, so here we have carbon. Okay, carbon. Carbon's in the second energy level. Okay. And so I can, being in the second energy level, I can very quickly write this if I didn't have the superscripts, because I know carbon's in the second energy level and it's all the way across in the P element. So obviously the 2s is going to be full, and then we got the 2p. Now, if I look at the periodic table, carbon is in group 4. It's in the second column of the P element, so I can put a 2 there. Okay, and there's a maximum of 2 electrons for the S, so I got that done. That's 4 electrons. The only thing to finish up is the 1s2. By default, it's 2 electrons. Okay, and so I have 2, 4, 6 electrons total, which is the number of electrons that carbon has. And its outermost shell, its valence shell, is energy level number 2. There's 4 electrons because it is in Roman numeral 4a on the periodic table. And that tells me there's 4 valence electrons that are in the second energy level, which of those 4 electrons, 2 of them are in the s orbit and the other 2 are in the p orbit. Okay. Now, the people in the elements in group 4 have the option. They're on the fence, so to speak. Okay. So I can maybe draw it like this. Okay. So this is the 4a. So this is the gain electrons. This is lose electron here. Okay. Group 4a, starting with carbon, they can go one way or the other, depends on the reaction conditions. They have 4 valence electrons. They can pick up 4, okay? They can pick out 4, or they can lose 4. They're on the hill. Now, when we talk about groups 5a, 6a, and 7a, guess what? They're on the right side of the hill. They gain electrons. Specifically, the ones in the group 5a, they gain 3. So they end up with a -3 charge. Group 6, they gain 2. Group 7, they gain 1 with an overall new -1 charge, okay? Because that's the number of electrons they gain. That is their charge. Group 3 over here, they lose electrons, so they end up with a +3 because they got 3 valence electrons. The 2a, they will end up with a +2 charge because they lost 2 electrons, and then the ones in group 1a will end up with a +1 charge. See how that works? And in the process of gaining or losing electrons, what is happening, the elements in group 5, 7, 6, and 7, by gaining electrons, they become isoelectronic with the noble gas in front of it, whatever level they're at. Okay, that could be neon, argon, krypton, xenon, etc. Whereas the metals on the left side, by losing electrons, they become isoelectronic with the noble gas behind it. Okay, so that table there gives you an idea of what kind of charge they would have, and furthermore, also will tell you about the name of the compound, because when these elements lose electrons, the metals lose electrons, the name doesn't change. For example, we get the sodium element /atom compared to the sodium ion. Okay, and if I need to distinguish the two, I would say either sodium element or sodium ion. One or two, that's it. But the main name, sodium, remains. Unlike the nonmetals, when they gain electrons, the name changes completely. For example, let's do nitrogen. This is nitrogen. Obviously, its name is nitrogen. But when it becomes an ion, it gained 3 electrons because it's in group 5. And the name becomes nitride. Okay? Oxygen becomes oxide. Okay? Fluorine becomes fluoride. Notice the IDE. And then chlorine becomes chloride, bromine is bromide, iodide is iodine is iodide. So oxygen, like it says, oxide, sulfur is sulfide, phosphorus is phosphide. Okay, so the nonmetals, they change their names, so that's why you end up with a name like sodium oxide, or sodium phosphide, or sodium any one of these, chloride or fluoride, et cetera, et cetera. So you're building up your database now with all the metals and all the non-metals you're going to put it together. And here's the interesting part: because they are losing electrons completely to become a negative charge or a positive charge, we put them together to make new compounds. Sodium, when it becomes an ion, has a +1 charge. Chloride, when it becomes an ion to chloride, has a -1 charge. I put them together to make a compound, to make a formula, and I put them together such that the positives cancel out the negatives. So I can put them, these two as an example, I can put them together as a 1-to-1. So the formula for good old sodium chloride is simply NaCl. Okay. Sometimes the nitride is like, for example, you might have nitrite, okay, and sodium you want to put together. Okay. Well, that means I need 3 positive sodiums for every 1 negative nitrite. So the formula becomes Na subscript 3N. And that is the formula for sodium nitrite. Okay. All right. Kind of jumped ahead a little bit, but that's okay. Kind of give you a preview of things that we'll be talking about. We talked at length about this. Again, we fill up in order of S, P, D, and F within the energy group. Okay. Notice that all seven levels have an S orbital. The P orbital begins with second energy level, and the D orbitals begin with the third energy level, and the F orbits begin with the fourth energy level. Okay. Earlier I mentioned, okay, think of group 1 and 2A as the S electrons, and this is what this color scheme tells you here. You got 2 columns for the S, S1 up front, S2, okay, the second column. And then in the middle are the D elements from D1 to D10. Note there's 2 electrons on the S, so I can put a maximum of 2 electrons. 10 electrons on the D, so I've got 10 columns with the D elements. Okay, with the F elements, I got 14. It's maximum number of electrons I can put in the the F is 14. And then in the yellow, we have 6 columns. So starting with group number 3 with boron, everybody there has 3 valence electrons. So it goes P1 all the way across to P6. Okay, so that in itself, recognizing that helps you. And using the periodic table helps you to discern, to figure out the electron configuration for literally any element on the periodic table. Okay. All right. Let's do sodium. Sodium is sitting right here. Okay. So it's in the second energy level. So I can very quickly go 1s, 2s, and 2p. It's in the third one, we're saying 3S and 3P, okay? Just by knowing where it's at. So the first energy level is full, so that's full. Then I come across the second energy level, that's my S or electrons, they're full. And the P, 2 Ps are full, so that's full. And then I come across the first column, which is 1. So here we're not using any P's, because P's, we don't need them till we get it to aluminum. All right. So that's the electron configuration for sodium very quickly. See how quick that was done just by where its position is. Okay. All right. Let's look at oxygen, which is right here. Oxygen is in the second energy level. So we got over here, so I can go 1s and 2s and 2p, okay? All right, because remember in the second energy level, I can put 2 orbits. Well, the first one is full of electrons, they get filled up first. Then I shoot across the S electrons, they get filled up. And now I am in the 1, 2, 3, 4th column of the p electrons, so I can put a 4 there. Okay. Count my electrons, make sure I got the correct number. I got a total of 8 electrons, which is what oxygen has. Okay. All right, let's do calcium. Let's find calcium. Calcium is right here. So we got 1, 2, 3, and 4. So we got 4 energy levels. So the first energy level, second has the 2s and the 2p, third has the 3s, 3p, and the 3d. Okay, we introduce that. Now, we may not need these. That's okay. I just put them up there so I can go very quickly to fill out my electrons. Yeah. Once I always advocate a systematic approach of solving these problems, and then you get to the point where you become very comfortable. You can, I not do some of these steps. Okay. So everybody is full for the 1s. Check that off. Everybody's full for 2s and the 2p. And the third 3s, that's full. And we shot up we used up all the 3p. Okay. And and then we got the 4th level, I forgot. 4s and 4p and 4d. Again, we may not need it. Now, the 3d we don't need because we are only going to go, this is the S, the second column. So this is 4s. So we don't need the 3d, not until we hit the next one in there. And we don't need the p or the next d in the 4th energy level because we stop right there with calcium. Okay, so I can just cross those out. I can rewrite 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Okay, and that's it. Now, the number of valence electrons calcium has is 4. That is the valence shell, the 4th energy level. It's not going to have the 4d, any electrons there, not until we get higher, with elements. So we can leave those out. Okay. And the D, we don't need until we start in here, which is not the question, number 21. So that's our electron configuration. All right. And then I'm working through each one individually. So we got chloride here. So again, 1, 2, and 3, third energy level. So we got chloride here. I can go 1s, then the 2s and the 2p. And then we got the 3s and the 3p. And the 3d is also playing in here. Okay, but do we need it? No, we don't, because the 3d is not necessary until we hit that guy. So we can forget him. So the 1s is full, the 2s and the 2p6 is full. Okay, we go across here, those 2 columns are full, the 3s2, and then we look and see the p's, p1, 2, 3, 4, and 5. And there's our electron configuration. Okay, for chlorine. All right. All right. Now, the other thing you can do if the question asks for is to do what's called a shorthand method. Okay. You don't have to write the electron configuration for everyone, but only do it if the question says not to do longhand. But what this demonstrates here is the longhand method. The shorthand method is quite simple. Let's go back to calcium. Okay. Well, we identified calcium, and then we identified the previous noble gas before calcium, and that would be argon, right? Okay, so we can write calcium, and then in brackets, we can write AR. Okay, two. And then we know that this is in the 1, 2, 3, 4th energy level, so it's 4s2. Okay, and so what this argon represents is this information right here. Okay, so not having to write everything out, the electron configuration. So you're welcome to do the shorthand method if the question says don't do the shorthand method. If it doesn't say anything about the shorthand method, more than welcome, that's acceptable. But sometimes we want to see you, we want to look at your answers and make sure that you understand how to figure out the electron configuration in longhand, okay? And you can do that for anyone. Just look at the previous noble gas, and then just fill out the next. And so what happens is when calcium loses 2 electrons, its valence shell is the 4s2. It loses that, and calcium becomes a +2 charge, and its electron configuration is simply isoelectronic with argon, okay, by losing 2 electrons. Okay. This is a slide where you can use their position in the periodic table. And what it lists there is the last part of the electron configuration for the element itself. Notice the p electrons over here, p1 all the way across to p6, okay? The coefficient 1, 2, 2, 3, 4, and 5, that represents the energy level, okay? All right here. And the D's, yes. For Chem 130, we're going to just do sequential from 1 through 14 if we have to do anything. Yes, you can see that in the real world that the data demonstrates that it's not sequential. It goes 2, 3, and then 4. Has a lot to do with electrons and all the other orbitals and so forth. But for us, it's just sequential. And the same is true for the F. Okay. Notice that they are 2 energy levels less from the energy level that they exist in. So they're in the 6 energy level, but the S come out to 4 and 5 respectively. Okay. Then of course we've got the D elements, the S1, S2. And that helps. Knowing that, you can quickly go to the periodic table and discern quickly the electron configuration for most any element. Yeah, in fact, for any element. And we'll do some more examples, read through this, and during lecture, I mean, the lab, I'm more than happy to go over it again and do some actual more examples. Watching it here sometimes can be a little bit challenging, but yeah. All right. And this, again, is just an overlap of where boron is. See, boron is 2p1 right here. Kind of give you idea of where the electron configuration is for each element. Okay, so when we talk about noble gases, again, we use the term, I don't know why, but we use the term happy. Now, I don't know if they're happy or not, but I do know that they're stable. Stable enough that they're very unreactive. And based on our model, the reason they are is because they have that magical 8 number of electrons around their orbital, okay? They have a full set of S and P electrons. Yeah. And they're very stable. It's a stable configuration. And that is the driving force of these elements to obtain that stable configuration, okay? Now, I mentioned to you what the valence electrons are. The valence electrons are the outermost electrons, the outermost energy level where these electrons exist. Those are the ones that are interacting with any chemical reaction. That's where all the action's happening, okay? And depending if it's a metal or non-metal, it's going to gain or lose those valence electrons to obtain that optimal configuration with 8 electrons around it in the valence shell. Okay. Take a look at phosphorus. Notice phosphorus is in group 5. Okay. And so we got 3s2, 3p3, which is right there. Let me draw this here real quick. Right there, 3p for phosphorus, dp3, and then of course you got the 3s2 full. The outermost shell is has 5 valence electrons. It is a non-metal. Being a non-metal, it will gain 3 electrons. Okay, it has room for 3 electrons in the p orbitals, and in doing so, it now has a new charge because it picked up 3 valence electrons. Note here, phosphorus, the element, okay, has 15 protons and 15 electrons. Okay, net is 0. Phosphorus, the ion, still has 15 protons, but now it has 18 electrons. Okay, for a net of -3. And we also changed the name of phosphorus to phosphide, IDE. Okay. And it can handle those two, first of all, because it's a non-metal. And as I stated before, put this in long-term memory, all non-metals gain electrons, all metals lose electrons. And the non-metal here gaining electrons, it's a lot more energetically favored to gain 3 electrons than it is to lose those 5 in the outermost shell. Okay, because now with 8 electrons around it, it's in a much more stable configuration. All right, here we have how many valence electrons? Well, we can write out the electron configuration, which is one way to do it, or we can very quickly look at its position on the periodic table. Doing the electron configuration, you can see that the valence electrons are the outermost energy level, which is the 3rd energy level. It has 7 valence electrons, is in group 5, 6, 7A, the chlorine. Okay. Beryllium has 2 valence electrons, and aluminum has 3 valence electrons in the 3rd energy level. 2 of them are in the S, and 1 of them is in the P. Okay. So chlorine has the capability of gaining 1 electron because 1, it's a non-metal, but it can only gain 1 to fill up the p orbital to give it a 3p6. And so when it does that, it has a net negative now. So now its electron configuration is as follows. Note the difference, it gained 1 electron. Okay, so it has a negative charge here. Now, when beryllium is a metal, it's going to lose its 2 valence electrons. Its net configuration will be, they have a +2 charge, and its new configuration simply be a 1s2. Okay. Aluminum, once it loses those 3 valence electrons, will have a +3 charge. And its new configuration will be 1s2, 2s2, 2p6. It lost those electrons in the outermost shell. Okay. And so what happens here is when we look at the radius, so let's take a cross-sectional picture of aluminum. Aluminum, to begin with, has the nucleus, and then it has 3 energy levels. Okay, there's 2 electrons in the 1st energy level. There's 8 electrons in the 2nd energy level, and there are 3 electrons in the 3rd energy level. Okay, 1, 2, and 3. Now, when aluminum loses those 3 electrons, its new outermost shell now is the two electrons in the first energy level is still there, but now it has 8 electrons in the outermost layer now, okay, by losing the 3 electrons in the outside third energy level. And so in essence, the ion shrunk in radius. By losing those 3 electrons, it is now smaller than the actual atom, okay? Whereas the nonmetals, by gaining electrons, when they become ions, they get bigger. So the radius of the ion versus the element for, say, chloride, the chloride will be much bigger in diameter because it picked up a negative charge, which is now being pulled apart from each other because there's 8 negative charges around the orbits, and they're going to negatives repel. Okay, so they get bigger. Okay, so there's one little trend about the ions and how they get bigger or smaller depending on their metal or non-metal. Okay. This is group number 4. This is the heel, if you will. Okay, so being on the hill, this by looking at the group number, and this is only true for those A elements, the 1A, Roman number 1A through 8A. You'll see in the innermost, those D elements, they have a B. They call those the B elements. We can't predict 100% their particular charge. They vary. They have a variable charge of, for example, copper could be a copper 1 or a copper 2. Iron can be an iron 2 or an iron 3. It varies. It depends on the conditions. And they can have multiple charges. The ones in the A are set. They're going to have a very specific charge once they become ionic. They're going to lose on the electrons from groups 1 through A, and then respectively have a +1, +2, +3 charge for the ions, okay? The group 4, well, they can lose all 4, give you a +4, or they can gain 4 more, have a -4. It can vary, depends on the conditions. After that, the group 5, you end up with a new ion by gaining 3 electrons, give you an overall -3, -2, -1, and obviously the noble gases always have a 0 net charge. They're not gonna, nothing's gonna happen to them with respect to gaining electrons. Okay, so knowing where they're at on the periodic table will aid you in determining what type of charge their corresponding ion will have, which then will aid you to figure out how many of each I need to put together to make a compound. Okay, because the note here is that when we deal with these type of compounds, ions, to make compounds, we have to put enough positives and enough negatives together such that the charges cancel each other out. Okay. Yeah, and don't forget helium. Helium does not have the 8. It has 2. All right. So here they ask you, how many valence electrons do they have? Well, it's a straightforward shot. You just find them on the periodic table. Find the group that they're in, and automatically will tell you that strontium is in group 2A. It has 2 valence electrons. Okay. Bromine is in group 7A, has 7 valence electrons. Argon is a noble gas, it has 8. Silicon, like carbon, has 4. Okay. And sulfur has 6. Okay. This is just for the elements themselves. When they become ions, that number will change. So here we're the driving force here is, again, why do compounds, atoms, I should say, make compounds? Why do they bond? Okay, simply because they want to have a noble gas configuration. That's the ultimate goal. So they're going to lose or gain electrons So they have a electronic configuration. Now, you would think with all the type of atoms that we use to make compounds that we would have a variety of different types of compounds, but there's only two types of compounds. Okay. The ones that we're going to be dealing with and talking about are called ionic compounds. And these deal with ions. Okay, hence the term ionic. And these deal with the elements that have lost or gained electrons. So when we put them together, we need to put them together with such that they have sufficient number of charges to cancel each other out. And so the ions, the elements, lose or gain electrons so they can get that electron configuration, okay, to become more stable. And then they come together such that you have enough positive charges to cancel out the negative charges. For example, we know that sodium ion has a +1 charge. How do we know that? Look for sodium on the periodic table. Okay, it's in group 1A, has one valence electron. It's a metal. It will lose that one electron, resulting in a +1 charge. Oxygen, when it becomes an ion, is a nonmetal. It is in group 6A. Okay, it's a nonmetal. It will gain 2 electrons to get that happy 8 configuration, resulting in a -2 charge overall. Okay, so we have to learn the charge of the ions that they create before we can put them together properly in the right ratio. Okay, so here we have one positive sodium ion and one ion with a total -2 charge. We have to put them together such that this tells me that I need 2 positives to cancel out the one negative charge that the oxide has. So that 2 becomes the subscript for sodium. So now the formula becomes Na2O. The name is sodium oxide. Okay. Oxygen oxygen became oxide when it became an ion. Okay. Now we did this with sodium, but you can take any metal, calcium, potassium, so on and so forth, and combine it with an oxide to make a compound. You can go back and forth. We picked oxide as the anion, the negative charge, but you could have done this with chloride, bromide, all of them. And just, you can see you start building up a database of all the compounds that you become more familiar with as far as making. But the ultimate goal is this. These are ionic compounds, okay? The octet rule is fulfilled because they lost electrons before and after to get the octet rule. And then they come together with a specific number of each, positive and negative, to cancel each other out, okay? Now, the unique thing about these ionic compounds and how they distinguish them from the other type of compounds, there's only 2 types. Ionic is one. Is that these ionic compounds, when you put them in water, they have a tendency to dissociate. They break apart. Some of them break apart 100% and just are very soluble in water. Some of them, not so much, maybe much, much less, but they do go in solution. And that's the thing is about ionic compounds. They will dissolve 100% or much less, but they will dissolve. On the other hand, the other type of compounds are bonds. These are ionic bonds I just talked about, but the other ones are called molecular compounds. They also see the term covalent compounds, and they make like I lost my train here. They make molecular compounds that make covalent bonds. Okay. Now, unlike the ionic bonds that have a full positive and full negative, the full positive and the full negative, they will react with each other and attract each other like 2 magnets. Okay. They don't form a true bond. There's no sharing between the 2. They form an attraction to each other like two magnets, and they form what's called an electrostatic attraction. Unlike covalent bonds, where there's an actual sharing, I make them analogous to my fingers. The ionic bonds are basically, they come together and they attract each other, and there's no exchange of anything between them. They just attract each other by the charge. That's an ionic bond. The molecular bond, they come in with the valence electrons, and they come together and they share electrons, and they actually form a bonded pair. There's a sharing, and a good example of that would be like water. Okay. Well, the criteria for a covalent bond is a combination of a non-metal plus a non-metal, NM non-metal. That's the criteria for a covalent bond. Notice hydrogen's a non-metal, oxygen's a non-metal. Unlike the ionic bond, which I didn't mention here, I should have got ionic bond. It is a combination of a metal plus a non-metal. And that's how you distinguish the two, like sodium chloride. Sodium is a metal, chloride is a non-metal, okay? Here, molecular compounds, they share electrons, and we're gonna learn that there's an equal sharing and an unequal sharing, which changes the property of the molecule, okay? We'll learn all about that down the road. So covalent compounds. Now, the other aspect is this. As I stated with ionic bonds, when you put them in water, they will dissociate in water, 100% or much less, okay? Covalent compounds don't do don't do that. And if I take carbon, another example is carbon dioxide. That's a covalent compound, two nonmetals. If I put that in water, it doesn't dissociate to you carbon ions and oxygen ions. They still go in solution, but they remain intact, okay? There's only one type of covalent bond that dissociates. I won't mention it here, but we'll talk about that down the road. All right. But the point of all that, what I just explained about what's coming up, is that whether it be a ionic compound or a molecular compound, the ultimate goal is to get eight electrons around, okay? And be it, they're going to share these electrons, bond them with something else, they're going to be shared. And the ultimate goal is to get 8 around electrons around themselves. No different than the ionic compounds that have created the 8 beforehand before they come together. All right. Here's an example of sodium, which has 11 protons and 11 electrons. Okay, and that's the electron configuration. What's highlighted in white is the valence shell. Okay, so the valence shell is 3s1. So sodium is a metal. It will lose that electron, resulting in now having one less electron, resulting in a charge of a +1. Okay. Because now it still has 11 protons, but instead of 11 electrons, now it has 10 electrons. So the new net charge is a +1. And guess what? Its electron configuration is that of neon. Okay, 1s2, 2s2, 2p6. Okay, it has the new ion has 8 electrons around it. That the 3s1 is now empty. Okay, and then the new valence shell is now in the second energy level, which is full, a more stable configuration than trying to maintain that 1 electron out there. And it's a big challenge for sodium to maintain it. It's so reactive that we have to store it in oil because it will react quite readily. All right. Now, at the other end of the spectrum, let's take sulfur. Okay. Sulfur's electron configuration is as follows. The ones that highlighted yellow are the valence electrons. There's 2 of them in the s, 3 of them in the p orbit. So it is in group 6a. Okay, so there's 6 valence electrons. It is a non-metal, so it's going to gain electrons. So because it has room for 2 electrons in that 3p orbital, and it will pick up 2 electrons and fill it up. Okay. And so now sulfur is isoelectronic with argon, because it shares the same number of electrons as argon. And now its new, by gaining 2 electrons, its new valence shell is full with the magical 8 number. Okay. And we also change the name. So sulfur becomes sulfide. And that's only true for the nonmetals. Okay. So this was sulfur, and it becomes an ion, it becomes sulfide. So we have to be very specific. If we make a compound with sulfide, then we call it whatever they call it, sodium sulfide. Okay, but we wouldn't call it sodium sulfur because that would be incorrect. Sulfur is the element. Sulfide is the ion. Okay, here you're being asked to write the electron configuration of the ions. And be careful here. Okay, if you ask to write the electron configuration of, well, point number 1, make sure that it's okay to write it shorthand if you want to do that. But the second thing is this. Make sure you're reading the question correctly, because here they're asking you for the electron configuration for potassium ion, not potassium, okay, but potassium. Because if it were potassium, see, that is the atom, and this is the ion. Okay, note the difference. The atom lost the valence electrons, group 1 is for S1, okay? So it becomes, the electron configuration becomes isoelectronic with argon. And so the point again is make sure you are reading and make sure that you want to write the configuration for the ion and not mistakenly write the configuration for the atom itself. And it does happen. Okay, ask you for the ion, but the students sometimes represent the atom itself, and vice versa. Nitride, okay. We have 1s2, 2s2, 2p6. Now, the nitrogen itself, before becoming that, would have been 1s2, 2s2, 2p3. And that is for nitrogen. Okay, note the difference. So nonmetal has room for 3 electrons. So we put 3 electrons in the p orbital, 2sp orbital, to give it this, which is isoelectronic. This is the ion, which is isoelectronic with neon. Okay. Then finally, the electron configuration for magnesium metal ion, excuse me, not metal, but magnesium ion, which is 1s2, 2s2, 2p6. So if you look at the position of nitrogen, its noble gas in front of it is neon. Okay, so by gaining 3 electrons, it becomes isoelectronic with neon. And if you look at the magnesium's position, it's in the 3rd period. Magnesium is in number 12. By losing 2 electrons, now it becomes isoelectronic with neon. Okay. All right. Now, this for fun, put some of these together. Earlier, I just demonstrated how we can start putting these ions together. So the name here becomes nitride. Went from nitrogen to nitride. The K and the Mg remain potassium and magnesium accordingly. So I want to combine the potassium and the nitrite. Note that potassium each has a positive one. So I need 3 potassiums for every nitrite. So the formula becomes K3 subscript 3N. And that is potassium nitrite. Okay. Now let's try to combine these two. We had the magnesium ion and the nitrite. Now, the order of writing the formulas always is the metal first. We write the formula followed by the non-metal. Notice I put potassium first, followed by the non-metal. Okay. So I wrote magnesium first, then followed by the non-metal nitrite. Now, how can I put these together? You saw how potassium is straightforward. You just add enough of one to balance out the charge of the other. But in this case, I have a -3 and a +2. What do you think I need to do to get these together to write a formula? It's a legitimate formula. They do come together to form a compound. But what do I need to do? Any suggestions? No suggestions? Well, let's take a look at the charges. I have a -2 and a -3. Okay. What would you do if I was trying to add these fractions of 1/4 plus 1/3? What would I do there? Any ideas for that fraction? Wouldn't it have to find a common value between the 4 and the 3, right? I don't need to convert. Maybe most of the time I multiply the 2 and my common factor is 12. So I can convert the 1/4 to 12 and the 1/3 to 12. And now I can add them up. Well, here's very similar here is that we need to find a common number, okay, between the 2, the +2 and the -3. And I have to put enough of each so they cancel each other out. So what if I put 3 of my +2s and 2 of my -3s? So wouldn't that give me a total of +6 for magnesium and then a total of -6 for the nitrite? Yeah, sure would. So now I can put them together with the right ratio so the charges cancel each other out. So these numbers I wrote in front now become the subscript. So I got magnesium, subscript 3, nitrite, subscript 2. And that is the formula for magnesium nitrite. Okay. Magnesium nitrite. And you'll find down the road, you'll find more examples of that. So just remember that, find a common value and it should work out for you. All right. Okay, we talked at length about this, but we're talking about ionic charges, and this is because of what the metal, if it's a metal or non-metal, whether they're going to gain or lose electrons. Okay, and so I rewrote here that group 1A, group 2A, group 3A, their metals are going to lose electrons. So respectively, the new ions that are made or created will have a +1, +2, +3 respectively. Okay, and sometimes you might see it written as Mg+2 or Mg2+. Makes no difference. It's the same thing, whichever you're comfortable with. Okay. And you don't have to put a 1 in front of a single plus. You just assume to be a 1. Okay. And with respect to the anions, they're going to gain electrons. So group 7A will end up with a -1 charge. And 6A will end up with a -2 charge. And let's not forget 5A will end up with a -3 charge. Okay, so nonmetals gain electrons. And by gaining electrons, they become negative ions, but they have their own specific name. Okay, a negative ion is called an anion. Okay, anion. Okay, so group 7A, 6A, and 5A respectively end up with a -1, -2, -3 charges. They do that again to refresh your memory is by gaining these electrons. Now they have the octet full. Okay, they fulfill the octet. Okay. Now, the metals that lose electrons, the name to distinguish them as far as ions is a general name, be it a negative charge or a positive charge. But if you want to be more specific, their names are as follows. For positive charge ions, which is basically all the metals, they are called cations, okay? And for negative charge ions, they are called anions. Now, remember, when they come together to make compounds, specifically ionic compounds, you have cations and anions coming together. You won't have two cations and two anions coming together, because just keep in mind, they're like charges, they're going to repel each other. All right. Okay, group 4A, again, they can have a charge that varies from -4 to -2. And finally, the group 8A, as again stated before, they're not going to do anything because they already have 8 electrons around. So across the periodic table, you'll see the trend +1, +2, +3. This is only true for the A elements, excuse me. Plus or minus -4, -3, -2, -1, and obviously noble gas is 0. Okay. So it does help to know where they're at, what group they're in, and whether it's a metal or non-metal, to help you understand or to determine what their respective ionic charge will be. Will they be a cation or an anion? Okay. So this case is, for example, lithium. Lithium ends up with a +1 charge. Okay. It's in group 1A. It's a metal. It will lose that 1 electron, hence the +1 charge. Magnesium also is a metal. Now you might want to, if you forget how to determine who's the metal, who's not, I refer you to the periodic table and that stair step. Okay. That stair step tells you that those are metalloids. Anything to the left of the stair steps are metals, except hydrogen. Hydrogen is a non-metal. Everything to the right of those stair steps are non-metals. Okay, so you need to refresh your memory in that so you can determine who's losing and who's gaining electrons. Magnesium is a metal. Find it on the periodic table. It is in group 2A. Okay. Therefore, it will lose those 2 electrons, those 2 valence electrons, giving you a +2 charge. Sulfur is a nonmetal. It is a group 6A. Being a nonmetal, it will gain 2 electrons, giving you a -2 charge. Bromine, nonmetal again, group 7, it will gain 1 electron. Nitrogen, group 5, will gain 3 electrons, okay, giving you a -3 charge. And aluminum, back to metals, is in group 3. We end up with a +3 charge. So now you can start putting together a lot of these compounds, okay? And create all kinds. You can go lithium sulfide, lithium bromide, lithium nitride, or aluminum nitride, aluminum bromide, aluminum sulfide, or of course, obviously magnesium sulfide, magnesium bromide, magnesium nitride. So, and that's just some of the metals. You use every metal that you have, put them together in that manner. But just remember, you want to put them together where you have the total number of like charges are equal. Yeah, sufficient number of positive and negatives to cancel each other out to create a formula, a compound. All right, let's do this. I got 11:52. Let's take a 20-minute break. I gotta get some medicine in me. My head's pounding right now. Right, and then let's just finish up this chapter, which is, well, we're almost there. Let's finish it. We're 2 more slides, I think. Okay, isoelectronic. I've introduced that term. Isoelectronic meaning has the same number of electrons as whatever element is striving to. It has the same number of elements of whatever element. If it gains electrons, then it's isoelectronic with something else. And the same is true if you lost electrons. Okay. In this case, our driving force is to be isoelectronic with noble gases. So the question would be, what atom is isoelectronic with magnesium? Well, the quickest way to do that is to find magnesium on a periodic table. And we're talking about magnesium ions, so it's +2. Magnesium's right here. So it's 2 valence electrons that lost it. So I just look for the previous noble gas, which is number 10. So magnesium would be isoelectronic with neon, the magnesium ion. With the nonmetals, you look for the noble gas in front of it because they gain electrons. For metals, you look for the noble gas behind it because they lost electrons. Neon. Isoelectronic with phosphide, that would be argon. I can't overemphasize the part is that the ions do not become that neon gas, okay? Magnesium ion does not become neon, nor does phosphide become argon. They become isoelectronic with their respective noble gas, meaning that they share the same number of electrons. And there's a table listing the electron configuration. Note that all of them are ions, so make sure you're writing the electron configuration with all of the ions. And then you can see here that the calcium ion is isoelectronic with argon, as the case with the chloride ion, isoelectronic with argon. The oxide and the aluminum ions are isoelectronic with neon. Okay. Looking at the new valence shelf, each one of these ions being positive or negative, they result in that magical 8 number, 8 valence electrons on the outermost shell. Okay. All right, so here's a selenium. What they're asking you to do is kind of refresh your memory about how many protons, how many electrons, and how many neutrons. Okay, you just look up selenium in the product table, you see that it has 34, it's number 34. So it has 34 protons, 34 electrons, resulting in 44 neutrons. It is a group 6A non-metal, okay? I almost said metal. So it will gain 2 electrons. So now it still has 34 protons, but it picked up 2 electrons and has a net -2 charge. Now it has 36 electrons. And the neutrons are the same. Nothing happened to the neutrons. Nothing happened to the neutrons. Nothing happened to the protons. In either case, be it an anion or a cation. If you look at aluminum here, aluminum has 13 protons, 13 electrons, and 27 neutrons. The ion aluminum has a +3 charge because it's a group 3A metal, and it will lose 3 electrons. So we have the number 13 protons, 10 electrons this time, and the same number of neutrons. Okay, well, that brings us to the end. And a chapter, I think I really need to do, chapter 6 is very short, and then we'll be done a little bit early. So let's take a 15-minute break, and then we'll come back to chapter, somebody raised their hand. Is that me? Oh, okay. Yeah, let's come back to chapter 3. It's very short. And we'll probably knock that out today, and then we're good to go. Chapter 6. Let's take a short, what time is that? I got 1:57. Let's come back at 1:20. Okay. All right. Okay, I'm back. Let me begin with, start off with the next chapter, which is chapter 6. It's fairly short. It deals with the periodic table. A lot of what I've talked about today, I'm going to regurgitate, as they say here, because I try to give you information that's, coming ahead to kind of put it all together at the end. So we're going to talk about the periodic table. And the periodic table, as we know it, is, way back in 1869, Dmitry Mendeleev, he was a Russian scientist. What he did was arrange the elements in the table of ordering or increasing, in the order of increasing mass. He put elements with similar properties in the same column, which is amazing to think about now. He realized that certain elements, the known elements, behave very similar. Power observation, because again, they didn't have all this fancy equipment to work with. So he put his first periodic table, which is shown here. And actually what happened, because the result of that there was a number of holes in the periodic table, which initiated other scientists to go search for those elements. And sure enough, the holes in his periodic table were over time, filled in until we discovered the majority of the elements that we have now, or all of the elements that we have now. Now, another scientist by the name of Moseley arranged the elements in order of increasing the atomic number, resulting in this periodic table here that we're more familiar with, okay? Now, along with that, we have what's called the periodic law. The elements in the column have similar properties. I hope that now you're understanding why they have similar properties, because they have the same number of valence electrons, they have the same number of valence electrons for those elements in the same group, okay? And hence very similar reactivity. Now, notice that the periodic table, the bottom group here, which has their own little name, the way it's put together, this is number 57. Let me show you this a little bit better here. Okay, this is number 57, and then it continues with 58 right here, okay? And the same is true with 89 going to 90 right here. So this whole section is basically taken out of this area here. But we're going to put it back in to show you how that periodic table would look with that information in. And it looks like that, okay? Now this is the long periodic table. But in essence, they took them out to make it, I guess, more practical to deal with. Notice the numbering sequence up above, numbers 1 through 18. That is a new numbering sequence that's being advocated rather than using the Roman numerals. So that's still out in the open, I think. I prefer the Roman numerals because it basically gives me more information concerning number of valence electrons, number of electrons they will gain or lose, etc. Okay, so that's a long periodic table. There's been other alternative periodic tables. There's a picture of a circular one. Yeah, kind of interesting looking. And here's another picture one of another one. Here on this area, in this section, it predicts the appearance of other elements. Okay, these are predicted to exist, and but more likely these are man-made elements that are striving. My last reading, I saw they were working on elements above 118. So who knows? You might hear something new here in a couple of years. That more elements have been made, and actually, if they do that, then we actually have another energy level number 8. All right. So Niels Bohr, as we talked about last chapter, talked about the electrons being in specific energy levels. Okay. And that kind of altered the shape of the periodic table somewhat. And the modern periodic table shows what we discussed about the P block and the S block and the D block elements shown here. Okay, we talked about this before. And now the horizontal rows are called periods. Okay, also they're the energy levels. There's 7 of them, but they have their own name called periods. The vertical columns are groups. So Roman numeral 1A is group 1. All exhibit similar properties being within the same group. Okay. Now, the ones that have the Roman numeral A, those are called the main group elements. The ones with the B after the Roman numerals, those are transition metals. Okay. And so here we have in yellow, we have the energy levels, which are called the period. And then the blue here represents the vertical columns, which is called the group or family. Here's another name utilized. Now, some of these elements have their own little specific name, or some of these groups. For example, the groups 1A, except hydrogen, are called the alkali metals. Okay. Group 2A are the alkaline earth metals. And then in the far right of the periodic table, where you start with fluorine and on down to chlorine, etc., is those are classified or named the halogens. Okay, and then of course you're familiar with the name of noble gases for the far right column in group 8A. Okay, the transition metals, or otherwise known, if you recall, the D block or the D group elements. All right, those are called transition metals. And they're not, with respect to their behavior and properties, very hard to be predictable with respect to how they behave and the reaction. Then down at the bottom, the 2 groups that stick out, you have the top there called the lanthanides and then the actinides, okay, in gray and in mustard color, respectively. So those are called transition metals. Now, the lanthanides and the actinides are actually also called the inner transition metals, right? Or another name for them are rare earth metals. So the lanthanides are here in gray, okay, and the actinides here in mustard color. Note that elements greater than or equal to 93 are man-made. Particle accelerators actually making these elements, hence their atomic weights are in parentheses. Okay. All right. So all of the actinides are radioactive elements. Okay. Now you may ask the question, for example, name an alkali metal in the third period. And that will be sodium. The group 1A are called alkaline metals. And then the third period, obviously, energy level 1, 2, and 3, sodium is sitting there. So that would be sodium. A halogen in the second period. So we go over to the halogens, which are group 7A. Okay. And the second period would be, it would have to be fluorine. And then noble gases in the fourth period would be 1, 2, 3, and 4. That would have to be good old krypton. Okay. And refresh your memory with respect to metals and nonmetals and metalloids. The ones highlighted in green are classified as metalloids. The ones in reddish color, pinkish color, I guess, for my computer, are the nonmetals, including, don't forget about hydrogen in the far left. Then everybody else are classified as metals. Okay. Now, with respect to the size of these, atomic size specifically of these elements, we're going to talk about the radius, the distance from the nucleus to the outermost electrons. Okay. Now, as you go down the periodic table, you're increasing the number of energy levels. So obviously it makes sense that as you go down the periodic table, the elements get bigger. Okay. So going down the periodic table, you got a bigger radius, you got a bigger element, okay? More energy levels. Now, when you go across from right to left, okay, the radius increases, or alternatively, going from left to right, the radius decreases. Okay. Now that's the ones, those elements being within the same period. You might think, well, why is that? You know, why is that happening here? Why is it, as we go down the periodic table, and that makes sense, we're just having a bigger element. Okay. But across from left to right, why would the radius decrease? Okay. Well, here's why. Because as we progress from left to right within the same period, okay, the number of protons increases. And having more positive charge, more nuclear force, the electrons are being pulled in much tighter. Okay. We increase the number of electrons, we increase the number of protons. So we're getting that nuclear force getting stronger, resulting in the electrons being pulled in closer together, closer into the nucleus, and therefore results in a smaller radius. Okay. So one way to kind of remember this is the snowman. As we go down the periodic table, you can see that the radius increases, bigger elements. Now take that snowman, drop it over from left to right. So going from left to right, the radius increases, because as we go from left to right, we increase the number of protons and the number of electrons. Okay. You take a look at your periodic table. Okay. And if you got it in front of you, you know, if you take carbon, I got 6 protons, and you compare it to a fluorine with 9 protons and 9 electrons. Well, carbon has 3 less protons and 3 less electrons than fluorine. And so fluorine, with having 9 electrons, 9 protons, their magnetic force, that nuclear force, is much stronger, resulting in that nucleus, the radius, I should say, decreasing in size. All right. So this is a general picture. Obviously, there's exceptions to the rule, but for us here, the general trend is from going down the periodic table, radius increases, and going from left to right, the radius decreases, or alternatively from right to left, the radius increases. Okay. Yes, of course, there's places, areas in there you can see a little bit of deviation from the general rule. All right, so you might be asked the question, okay, I got these 3 elements, all right? Which one is bigger? Which has a larger radius? Well, to answer that, you first have to find them on the periodic table to answer your question. You can see here that these 3 elements are within the same group, specifically group 6A. Therefore, that means that TE is a lot bigger, okay? Because it is in group 5 versus group 2 of oxygen. And so TE is a lot bigger. Next question, going from magnesium, silicon, and sulfur. So find them on the product table. First thing we note is that they are in the same period, okay? And being in the same period, the difference here is this, that we are going from left to right, is going from metal character to non-metal character. Keep it in mind that non-metals want to gain electrons. And so what's happening there is electrons for non-metals are being held, wanting to be held a little bit tighter, and are held tighter than those of metals, okay? Plus the fact that as you go from left to right, we increase the number of protons and electrons, resulting in increasing the number of the nuclear force, if you will. And so resulting in sulfur being much smaller in radius than magnesium or silicon, okay? Because these electrons are pulled in a little bit strong, a little bit tighter. So we do have the videos on the atomic size. So, you know, getting an alternative viewpoint, Dr. Kim Smith, who's back there, she will be, Dr. Kim Smith is the one in charge of our department, at least at GCC, and she has made all these videos. So you have my stuff plus her stuff, so you should have a lot of information. Okay, let's briefly talk about ionization energy. And guess what? We're almost done with this chapter. I think we'll call it a day. Okay. What ionization energy is a measure of removing an electron from a neutral atom. Okay. So we have a neutral atom and we find a way to remove an electron from it. Now, common sense, think about it. It will tell you this, that those atoms that hold on to their electrons tighter, I would anticipate that the amount of energy to remove an electron would be pretty high. We can remove electrons from all these atoms, but it's just a matter of energy. And if the electrons are being held on tightly, then it's going to take a lot more energy to remove them, okay? But the general step or description in the reaction mode, if you will, is given here, where you got sodium undergoing ionization energy to remove an electron, so to generate the sodium ion plus its electron, okay? Now, given what we talked about metals versus nonmetals, I stated earlier that nonmetals more readily give up electrons compared to, let me restate that, metals lose electrons more readily than nonmetals, okay? So metals want to give up their electrons compared to nonmetals. So that in itself should suggest that if I put a measurement and try to measure how much energy it actually takes to remove an electron, I would anticipate that the ionization energy for metals would be much less than those for metals, non-metals, okay? Because metals want to give them up electrons, non-metals do not, okay? So we would expect their ionization to be, okay, here's my dog trying to get me to play with him. Sorry, gotta go play. So the trend is this, going from left to right, the ionization energy increases. Ionization increases going up a group. So going up within a group, and if we compare, let's say, something like sodium versus potassium, well, potassium is a bigger element, larger radius. Its electron is a little bit further away, and it's got one electron, but everybody's in the same group as compared to, say, lithium, okay? Lithium's lone electron is closer to the nucleus than it's a cesium, where its lone electron is much further away in the 6 energy level versus the 2 energy level for lithium. So it stands to reason that cesium, to remove its electron would be much less energy than that of lithium, because lithium's lone electron is closer to the nucleus, and that force is a little bit stronger than the force of an electron that's much further away from the nucleus. Okay, so it makes sense that the IE increases up a group or decreases down a group, whichever every which way you want to look at it. Now, going from left to right, the IE increases. Okay, metals have low IE because they want to lose electrons. That is their goal. And by losing electrons, they will be isoelectronic with the normal gas behind it. Whereas nonmetals have a higher IE because they don't want to lose those electrons. You know, their orbits, the outermost valence electrons are almost full. You know, and so if we can fill them up more to get a better electronic configuration, they prefer that. And so they prefer to gain electrons. So that results in nonmetals having higher IE than the metals. Okay, so the general trend, if we plot that data, is as follows. And if we look at, start right here, that's hydrogen. Starting here is hydrogen. And if we go across the periodic table, you get to helium. Because you can see that going from left to right, the ionization energy goes from about 14, about 13 and a half, all the way up to almost 25. Quite a big jump, okay? Because helium has a noble gas configuration. It's duet rule has been fulfilled. It's not going to give up that electrons very readily as compared to hydrogen. Then we start off with lithium down here, at number 3, and then we'll go across the neon. You can see the general trend. The general trend, again, you start off with about 5 energy units, and you go up to about 24 energy units, 23, 22 energy units of neon. Okay, so that's going across the periodic table. Those electrons, you go from a non-metal region to a metal, a metal region to a non-metal region, and those electrons want to be held down a lot greater than the ones from the metals. Plus, as you go across the periodic table, you're increasing the nuclear force, increasing the number of protons, increasing the number of electrons, so the radius gets smaller, and those electrons are being held down tightly. Okay. And then you continue across the periodic table, go back to from lithium, go to sodium, and then across to argon. Notice the trend continues. Now, as you're going down the periodic table, you can notice the general trend as you go across the periods. The slope of the line gets to be, smaller and smaller. It gets less and less. Eventually, almost a flat line. But that's the reason, because as you go down the periodic table, the elements themselves get bigger. And so those electrons, be it metal, non-metal, the trend is still to take more energy to remove an electron from a non-metal than from a metal. The trend is still there, but the magnitude is a little bit less because you're getting bigger elements overall. Those electrons are further away from the nucleus. The amount of force to hold on to them is much less, okay? And that's why you see that slope start to get less as you go down the periodic table. All right. Okay, so question here, which has a larger IE and why? So if we look at these 3, chlorine, aluminum, magnesium, okay? Well, the first thing you should notice that here, we're dealing with 2 metals and 1 non-metal. The fact that you got 1 non-metal automatically tells you that definitely the chlorine, the non-metal, would have the higher ionization energy, simply because the fact that it is a nonmetal as compared to aluminum and magnesium. Okay, so chlorine would hold on to their electrons with a much greater force than the metals. Its tendency is to gain electrons. Now, going down the periodic table, lithium is the smaller of the three here. Okay, and being smaller, where everybody's within the group, being the smaller one, its electron is closer to the nucleus. So therefore, its electron is being held on to itself, which is much greater force than the other larger atoms, and therefore will require more energy to remove an electron. Okay. Again, there's YouTube videos on the site concerning this from Dr. Kemp. You may want to read it. Now, this aspect, this property here is very important. It's going to show up over and over again when we start talking about bonding, and specifically a specific type of bonding, molecular bonding. Okay, not ionic bonding. Ionic bonding we dealt with positive and negative charge, but when we talk with molecular bonding, there is a sharing of electrons. I didn't elaborate on this, but that sharing encompasses two types of sharing. One is an equal sharing. Think of it as a tug of war. There's an equal tug of war that those electrons are being shared evenly between two atoms. Then there is an unequal sharing. The unequal sharing results in the electrons being pulled closer to the element that has what is called a higher electronegativity value. Okay, that in itself causes properties for a compound, makes it for what we're going to talk about, whether a bond is polar or non-polar, which affects the physical properties of a compound. And what I mean by polar, non-polar, think of it as at this time, think of it as water-like versus oil-like. And that is why certain things don't dissolve in oil, because they tend to have polar water-like properties, and vice versa. Okay, and that's related to the electronegativity involved with the atoms in that bond. Okay, now what we do here, the general trend is that you go from left to right, the electronegativity increases. And as you go from bottom to up, the electronegativity increases. What in essence we're using here as a guideline to help you is the element fluorine, which should be about right here. Okay, fluorine, change that color. Fluorine is the most electronegative element there is, and that is our benchmark, if you will. That is our guideline to determine if we're doing a compare and contrast between two different elements other than fluorine. Who's the more electronegative? We determine who's more electronegative by its position relative to fluorine. Anything closer to fluorine makes it the most electronegative, resulting in, if there's a bond between two different elements, the most electronegative will pull the electron density toward itself much more than the other. For example, if you look at carbon and nitrogen, okay, and if there was a bond between them, we need to determine, first of all, this is a molecular bond because it's made up of nonmetals, okay? And the second part is this, well, what's the electronegativity of each one of the elements? Well, we find its position in the periodic table, and it's approximately, let's say carbon's about right here, nitrogen's about right here, ballpark. The point being that nitrogen is closer to fluorine than carbon is. That tells you that nitrogen is a lot more electronegative than carbon, which then tells you that that bond right there between them is not shared equally, okay? It is being pulled more so to the nitrogen side than it is to the carbon side. Unlike a bond where you have the elements are the same, let's say carbon-carbon, where the two elements are the same, so there's an equal sharing of that bond, unlike this carbon nitrogen where there is an unequal sharing of this bond. And being unequal means that the nitrogen being more electronegative, which we determined to be the case because his position relative to fluorine makes it more electronegative, means that in that bond, it will pull the electron density toward that. And we draw a little arrow going from carbon to nitrogen. There's like a little positive tail on that arrow. And the result is that nitrogen has what we call a partial, we make the symbol partial negative charge, and carbon has a partial positive side. Unlike the ionic bonds that have a full positive charge and a full negative charge, in covalent bonds, there are either no charge at all with respect to the bond because it's equal sharing, or there is a partial charge and results in a what we call a dipole, D-I-P-O. Now you're familiar with dipoles, they're all around us. Dipoles like a battery, you got a north and south side. It's two poles. The earth is the dipole. You got the north side and the south side, okay? Batteries, we got a positive and negative. That's a pole, dipole. The result is here, the same thing. We have a dipole. We have a partial negative on the nitrogen because nitrogen has a higher electronegativity than carbon, which then has a big effect on the properties of that compound that contain this particular bond, okay? All right, so noble gases don't have any electronegative values, again, because, you know, the octet is full. They're not gonna do anything to form any bonds, okay? So that ends this chapter. I want you to really focus on electronegativity because they will come back time and time again. Okay, they'll come back, and it's very crucial because with the electronegativity involved, it will tell us what kind of polarity a molecule will have, and that in effect tells us about the properties of that molecule. Okay. All right. So that ends the chapter. And you know what? Let us stop it here. Chapter 6. We'll continue with chapter 7 next Wednesday, and maybe 7 and 8. And then on Friday, we will also I'll talk about the gases, chapter 16. Okay. So, all right, let me stop it here.